This is Canvas Module 11.01, Introduction to Types of Acids and Bases. So a lot of this is going to be review for you from Canvas Module 4. So the Arrhenius definition of acids and bases is the most simple one, and it says acids dissociate to generate H+ ions in water. For example, HCl, aqueous, will dissociate to form H+ aqueous plus the chloride ion, aqueous. And this will go 100% because this is a strong acid. Likewise, nitric acid, HNO3, will dissociate completely to form aqueous hydrogen ions and aqueous nitrate ions. We learned in Unit 4 that strong acids dissociate completely to hydrogen ions and anions in water. What we add to that now is that means that K is very large because the equilibrium lies largely to the product side. There are 6 strong acids that you should have memorized previously. They are listed here: HCl, HBr, HI, HNO3, H2SO4, and HClO4. Notice HF is not a strong acid. So let me write here, not HF. This is a common mistake that students make. HF is in fact a weak acid. Weak acids dissociate only partially to hydrogen cations and anions in water. Assume all acids, but the 6 strong acids listed above are weak. In other words, K is much less than 1. So I have an example of 2 weak acids here. The first is acetic acid. Notice that I have drawn it so that the equilibrium arrow is pointing much more towards the reactant side because very little dissociation actually takes place. Likewise, hydrofluoric acid only dissociates partially in water. And what I have drawn here is what we mostly have is the molecule, okay? So most of the HF stays in the molecule form. And it's actually really incorrect that I have drawn these like this, but what the point that I wanted you to see here is that most of these weak acids remain in the molecule form. Now, remember that acids are electrolytes because they form ions in solution. Strong acids are strong electrolytes, and weak acids are weak electrolytes. The more ions you have in solution, the more electricity that solution can conduct, as that little drawing shows. All right, so that's acids according to Arrhenius. Bases dissociate to form hydroxide ions in water. So I've written the example here of sodium hydroxide dissociating to form sodium ions and hydroxide ions. Calcium hydroxide would dissociate to form the calcium 2+ ion, and it would form 2 hydroxide ions. So remember that this 2 here means that you're going to have a 2 when you have the dissociation. You need to use that as a coefficient. The Bronsted-Lowry definition of acids and bases is more general. So the Bronsted-Lowry definition says that acids donate protons, that's a hydrogen cation, to other species, whereas bases accept protons from other species. So in this case, I have HCl reacting with H2O, and I've got a one-way arrow because this is a strong acid. What is going to happen is one of these protons is going to get donated to the water molecule. And so we end up with the hydronium ion here and a chloride. Let's go ahead and put in the Lewis dots that we would see here. What actually happens is one of the lone pairs on the H2O forms a new bond to that hydrogen ion. Let's take a look at another example here. We have, let's label these. We've got an acid because it was the proton donor. We have the base because it was the proton acceptor. Another point I want to make here is H3O+. That's the hydronium. A lot of times this is just written as H+, so view them as the same thing. H3O+ is actually much more accurate. Hydrogen ions do not float around by themselves. They actually are always going to end up bonding with a water molecule. So think of them as the same thing. You can pretty much use them interchangeably. Okay, let's take a look at this next reaction. In this case, we have ammonia, NH3, and it is put into water. And so we're watching what happens when it's put into water. Notice that this time water donates a proton. So ammonia is our base because it accepts a proton, and water, in this case, is the acid. So look at that. Water acts as both an acid and a base. Strong bases dissociate, we also say protonate, completely in water. The only strong bases are the group 1 hydroxides. So you've got lithium hydroxide, sodium hydroxide, potassium hydroxide, etc. You need to memorize this. You also need to memorize that NH3 is a weak base. The video link to strong and weak bases, we'll view that separately. All right, let's keep going. We also have something called polyprotic acids. Polyprotic acids have multiple acidic hydrogens. The hydrogens dissociate stepwise when the acid dissolves. Some common polyprotic acids include sulfuric acid, phosphoric acid, and oxalic acid. So let's take a look at a stepwise dissociation. We have sulfuric acid, and notice I've written that that is 100% because H2SO4 is a very strong acid. So it's going to dissociate completely to form the H plus aqueous and the HSO4, and I should have put and included an aqueous after that. Now, in turn, the HSO4 minus can lose an additional proton. But notice here that I have shown it on both sides because most of it stays in its protonated form. So I've written that we have both of these present. And so we have a net reaction where H2SO4 is in equilibrium with hydrogen ions, the hydrogen sulfate ions, and SO4 2- ions. What I want you to take home here is that the dissociation is stepwise. Okay, let's take a look at carboxylic acids. So we have looked at carboxylic acids before. They have the general formula of RCO2H. So look out for that CO2H, and they always end with oic acid. Carboxylic acids are always going to be terminal groups, meaning they're at the end of a chain of carbons. They can form weak intermolecular hydrogen bonds with each other because they have OH bonds. They are all weak acids. They should be written in the molecular form for any net ionic equation. So notice that I told you that the hydrogen always comes first in an acid. Well, that was not the complete truth. For the carboxylic acids, it's always that terminal hydrogen. So let's circle them in these structures that we have. And while we're at it, let's add some dot structures to complete octets. So I'm completing octets. This is the hydrogen that can be lost. Here's the hydrogen that can be lost. Here it is on the structure. You should be able to draw a Lewis structure of an acid for the AP exam. Here we have benzoic acid. Here is the hydrogen that is acidic. So the term that we use for this, there's a nice one right here, is we say that it is the labile hydrogen. It is the hydrogen that can be lost. So I also have shown here an image of the dissociation of acetic acid. So we have a water molecule. Okay, so we've just put acetic acid into water, and this is showing you what happens. That hydrogen is going to transfer over, and now we have formed the hydronium ion. And let's finish putting our lone pairs on here. When the hydrogen left, it left one of its electrons with the oxygen. So this whole structure carries a -1 charge. In this case, this is the acetate ion. So we have acetic acid and the acetate ion. So the labile proton is single bonded to the oxygen on the CO2H group, okay? You need to memorize which hydrogen can be lost. So memorize which hydrogen is acidic. Okay, so those are our carboxylic acids, so you should recognize those as being acids. Amines are something that you should recognize as being bases. So we're going to talk about amines. So amines are a class of compounds that have a nitrogen in them with 3 other bonds leading to it. And so I've got the general formulas here. So we have RNH2, R2NH, R3N. And you go, well, what the heck's R? Well, R can be anything. It is, well, let's say anything. It's a group. The R's can be the same or different. The amines are bases because the nitrogen accepts a proton on the lone pair. They can hydrogen bond if they have an NH bond. So let's take a look at amines and identifying where they are on a molecule. So our first one is ethylamine. Look for that NH2. There we go. It's right there. Dimethylamine. Trimethylamine, it's missing its lone pair here. Okay, we know it would have a lone pair because we have to fulfill the octet root. And then pyridine. So all of these have a lone pair. So look for a lone pair on the nitrogen. To accept a proton. These are called nitrogenous bases. So I have here an example of a 3 R's on a nitrogen reacting with H2O. And you can see that the H2O gives up one of its protons to the nitrogen. And so we generate a hydroxide, and then we have a protonated nitrogen base. So remember, R can be anything, including H. Let's take a look at one last class that you just need to be a little bit familiar with. Just don't get thrown off by them. Amino acids have an amine and a carboxylic acid group, meaning they can act as both an acid and a base. They form intermolecular hydrogen bonds with each other and water. So if we look at this drawing here, here we have our carboxylic acid group. That's our acidic hydrogen. Let's find it on the other molecule. There's alanine. There's our acidic hydrogen. Also on here, we have an amine. So there's our amine. And we would have a lone pair. So lone pair can accept a hydrogen. There's another amine here. And again, we would have a lone pair that can accept a hydrogen. So both locations. All right, so we're going to stop there for 11.01. We've talked about Arrhenius acids, Bronsted-Lowry acids, carboxylic acids, so you should be able to recognize those, and then the nitrogenous bases.